All right, we're being recorded.
Professor, just a question.
Yeah.
Will there be class on Thursday?
No.
Okay.
Yeah, that will be the midterm. And so at the normal class time, we'll distribute the midterm. Let's see. Yay. All right. Can you guys all see that?
Yeah.
All right.
Yeah.
Great. Okay. So, okay. So today we'll be talking about a new, something new. I know it's a little awkward. It's right before the midterm. It's like you guys don't feel like learning anything new. I know that feeling, but you know, the show must go on. So today we'll be learning something new. Trying to get psyched up for it. And it's actually pretty cool. It's called the variational method. So that's the big plan for today, is to discuss this new topic. I just want to say, sometimes it's called, I don't know, I actually never see this, but sometimes you see it called the Rayleigh-Ritz method. But actually you don't see that very often, maybe back in the old days. Okay, so this is a new approximation for solving this Schrodinger equation. And I would say that this technique is not as useful as perturbation theory, but still very, very important. It's very, very important. It's not quite as useful as perturbation theory, but still very, very important. And like, for example, there have been various Nobel Prizes won using this variational method. This is how people solved the problem of superconductivity, for example, was solved using the variational method. But I won't get into that. Okay, so let's just discuss what it is, the variational method. And so let's discuss the main idea. And it's actually pretty simple. It's so simple. It's surprising how powerful and useful this is, but it really is. So let's consider a system that's described by some Hamiltonian. And so then what we want, what we can get from the variational method is we want the ground state wave function and we want the ground state energy. So the variational method is really useful for getting the ground state. It's useful for getting the ground state of a system. And so the idea then is, so if we have some system described by some Hamiltonian, then the idea is that if we have any normalized function, for any normalized function that I can write as psi of r, and of course when I say a normalized function of psi of r, you should think in your head, oh, that's some arbitrary state. Let's call that. So suppose it's just some arbitrary wave function. So for any arbitrary wave function, if I calculate the expectation value of the Hamiltonian for that wave function, which we can write as psi h psi, which you guys know, some integral psi star of r, let's just say in 3 dimensions, h psi of r, if I calculate this expectation value of the Hamiltonian for that state, then this expectation value is greater than or equal to the energy of the ground state, the true ground state energy. So that's the principle, and so what that means then is that what this means is that we can pick arbitrary. We can pick any wave function we want, an arbitrary wave function, and then the expectation value of the Hamiltonian for that wave function gives us an upper bound on the ground state energy. So the expectation value of the Hamiltonian is equal to an upper bound on the ground state energy, and that's it. That's the whole thing. That's the foundation of the variational method. So it's really simple. It just means that if we pick an arbitrary wave function and we calculate the expectation value of the Hamiltonian, then we can get an upper bound on the ground state energy of that Hamiltonian. And you might think to yourself, wow, how useful could that be? But it turns out to be incredibly, super, very, very useful. And so rather than me explaining why it's useful, it's most useful to just do some examples. But before doing the examples, let's do a proof. Let's prove this statement mathematically, because this is so important that let's prove it. And once we prove it, then we'll prove it, then we'll use it. So the proof is pretty straightforward. Let's prove it in 1 dimension, and you could generalize it into 3 dimensions. And so let's suppose we're given some Hamiltonian. Then we know that there must exist, even if we don't know these functions, we know that the eigenstates exist. We know that there must exist some eigenstates, I'll call them phi sub n, such that h phi sub n is equal to En phi sub n. Even if we don't know what they are, we know that they exist. Okay, and so then let's calculate the expectation value of the Hamiltonian. And so let's calculate it for some psi, but let's pick an arbitrary psi. And so let's pick an arbitrary wave function, arbitrary psi, and the arbitrary psi I can write as a expansion of the energy eigenstates, because they form a complete set, right? These are a complete set, orthonormal set, and so I have my I have my arbitrary wave function. So any psi, any state can be written as a linear superposition of the eigenstates of H. And so now let's calculate the expectation value of the Hamiltonian for this arbitrary wave function. And so I have to calculate it's psi H psi is equal to psi star H psi. But now I have to plug this in, and so to do this integral, it's going to be the integral from -infinity to infinity of psi star, and so I'm going to use this expansion, n psi c sub n star phi n star, which is going to be a function of x. I have h, and now I have the other one, psi. That's going to be psi star And now I'll have psi. And psi is going to be just, I have to pick a new summation variable. It'll be Cn prime phi n prime of x dx. Okay, so that's the expectation value of the Hamiltonian. And now I just have to do that integral. So let's pull out the summation sign. So I can pull the sum out and pull these guys out of the integral. Okay. And then I have my integral, phi n star of x, h, phi n prime of x dx. Okay, so far so good. But now the question is how to go further is not completely obvious, but let me ask you a question. What happens when h hits this state? What does h turn into?
En prime?
Exactly. So this whole thing then becomes simpler. It becomes n prime, c star n, cn prime, en prime, and now the integral becomes simpler. It's phi n of x star, phi n prime of x dx. And what is this equal to?
The Kronecker delta of n and n prime?
Exactly, because there are, or exactly, because the eigenstates of the Hamiltonian are orthonormal. That's exactly right. So it's the Kronecker delta. So we just plug that in. And so this thing is equal to then this n prime, c star n, c prime. I got my e n prime, I got my Kronecker delta. And now, of course, whenever you have a Kronecker delta, it collapses the sum. So that means that n prime goes to n. And so this sum now becomes sum over n, c star n, c n, e n, which is equal to sum over n, c n, magnitude squared, e n. And now we do a little trick, because now we realize that if I compare en to the ground state energy, what is the relationship between en and the ground state energy?
Greater than or equal to?
Exactly. En is always bigger or equal to the ground state energy. So this thing has to be greater than or equal to this thing. The ground, if I put the ground state energy there. Does that make sense? So just a simple thing. But this means that this means then that the remember what we were calculating was the expectation value, and that means it's greater than or equal to, and I'll bring the ground state energy out front, and it's going to be the sum over n Cn squared. But what's the sum over n of Cn squared?
1, because they're probabilities.
Yeah, exactly. And if you guys don't remember that, I can just, I don't know if it's worth showing it or not. Does anybody want me to prove that this thing is equal to 1? Does anybody want me to prove that? I'm happy to prove it. Okay, but I guess nobody needs me to prove it. That's from last semester, so just say something if you want me to prove it. I'm primed and ready to prove it. Okay, but nobody wants me to prove it. Okay, so then that means that h, the expectation value of the Hamiltonian, is greater than or equal to the ground state energy. QED, we did it. It's really a very cute little proof. I like that proof a lot. Just so simple, just boom, boom, boom. So that's very cool. Okay, so that is the underlying principle of the variational method. And so the question you might wonder is, how could that possibly be useful for anything? But it is incredibly useful, much more useful than you might ever expect. So so here's the thing. I'll tell you the trick. So why is this useful? The trick, so here's the trick. The idea is that what happens is that if somebody gives you, let's see if I wrote, okay, so the trick is to, if you're given, actually let's do it like this. This is why it's useful. If someone gives you some weird Hamiltonian that you have no chance of ever being able to solve, it's too hard. If you're given this and then they say to you, what's the ground state wave function? What's the ground state energy? Then what you can do is you can just guess some arbitrary wave function. Like if this is a 1D problem, you can guess some arbitrary function of x, but you can also have some variational, variable, a variational variable, a variable. And so, and then what you do is you guess a wave function and then you calculate h. And if psi is not normalized, you don't even have to normalize the wave function, because what you can do, if psi is not normalized, then you can calculate because h is always equal to psi, the expectation value, divided by this. So this ensures the normalization. So you often will see it written like this, because people often write the expectation value like this, because this is what works if your psi is not initially normalized, and this automatically normalizes everything. And so you guess the wave function, you calculate this, but then what you've actually calculated is the expectation value of h as a function of this variable lambda. And then what you do is you can minimize h with respect to lambda. So you can say, what's d h lambda d lambda equals 0, and then you can find lambda minimum, then plug it back in. Plug back into h lambda and psi lambda, and this becomes your ground state upper bound, and this becomes your ground state wave function. You see that? That's the trick. I just said it. That's the whole trick, what I just said. You pick a random function of some random variable, you plug it into the formula for expectation value, you grind through the algebra, you minimize that function with respect to the variable, you plug the minimum variable back in, and that's your answer. Now, if that doesn't make sense, let's do some examples. Because it's the kind of thing that's actually easier just to understand from an example than to actually look at the thing. Okay, let's do an example. Let's solve the simple harmonic oscillator problem. And you know that the simple harmonic oscillator is actually a pretty hard problem. I mean, you did it 2 ways last semester, I think, depending on who taught your course. You can do it the brute force way by solving the differential equation, or you can do it the very clever ladder operator way. Either way, it's pretty tricky, and it's the kind of thing that you wouldn't have figured out how to solve on your own, probably in a million years, unless someone tells you how to do it. Okay, but let's solve it now using the variational principle. And so here's the Hamiltonian. So somebody gives you this weird Hamiltonian. They say, hey, check this out. Suppose I have this. This is my Hamiltonian, p squared over 2m, kinetic energy plus potential energy, 1/2 kx squared. So that's the simple harmonic oscillator, right? That's the spring. That's the potential energy of a spring. And so we see that the Hamiltonian is equal to negative h bar squared over 2m, because that's the kinetic energy, dx squared, plus, and I'm going to rewrite it like this, 1/2 m omega squared x squared where omega is equal to square root of k over m. Okay, so this is my Hamiltonian, and so now I'm asking you, what is the ground state energy, and what is the ground state wave function? Okay, that's what I'm asking. And so now normally this would be a super hard problem, and you couldn't just use perturbation theory. There's no perturbation here. So there's, perturbation theory doesn't work. So now we'll use variational principle. Variational principle. And so the first thing you do with the variational principle is you guess a solution. Guess a solution. And that might seem really weird to you because you're not used to it, but it's not so hard. Because look, let's look at the potential. And so here's the potential, right? It's a parabola. All right, that's V as a function of X. Okay, so now let's just say that let's pick an energy. So suppose that this is the energy. Ground state, because the ground state has to have some energy. It's got to be somewhere, so let's just assume it's there. And then let's ask ourselves, what do we expect the wave function to look like? So there are three regions. I got region 1, I got region 2, I got region 3. What does the wave function look like in region 1, in region 3? Here. What does the wave function look like here? First, I will tell you, look, V is here. And in this region, I have that the potential energy is bigger than the actual energy. And so that's the forbidden zone, like in Planet of the Apes, the forbidden zone, the forbidden region. And so what does a wave function look like in the classically forbidden region? Somebody tell me.
A decaying exponential?
Exactly, it's decaying, right. And so the same thing is happening here in region 1. So that's also a forbidden region, V greater than E. And so here also I expect it to decay. And what do I expect it to do in this region? This is the good region. Here, region 2, I have E is greater than V. And so what do I expect it to look like in that region? Somebody tell me. What does a wave function look like when your energy is bigger than the potential energy? What does the wave function do?
It oscillates.
Exactly, it wiggles. That's exactly right. It goes, wiggly, 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 wiggly. Right, so we sort of already see what the wave function is going to look like, even without solving it. But for a ground state, how many wiggles are there going to be?
Half a wiggle.
Exactly, half of a wiggle. That's how you always get for a ground state. So this is what I expect. So immediately you can see that your ground state function should look like this. It's some kind of function that looks like that. Now we all know the answer. It's actually a Gaussian function, but suppose we didn't know the answer, but even without doing any math, we can just see that that's what my wave function should look like as a function of X. And so what we'll do then is this is intuition. So based on this intuition, we'll just say, okay, I know it should look like that. So let me do this. Let's pick the simplest function that gives me that kind of behavior. And so let's suppose I have this, an upside down parabola. So let's just do an upside down parabola. And so this will be my guess, my guesstimate. And so let's just call this, and then this part is 0. And this we'll call some place, we'll call A, some position A, and some position minus A that I don't know yet. And I'm just gonna, and so I'm gonna guess that my wave function is equal to this. I'm gonna make this weird guess. I'm gonna say, well, suppose it goes as A squared minus X squared, which is an upside down parabola, which hits, but now I'm gonna square it. So this is just some weird function I just made up. I actually didn't make it up, I copied it out of a book. But let's suppose that it looks like this for x less than or equal to a in the inner region. And what do you think my wave function is equal to for x greater than a? Somebody tell me.
0.
Exactly. So that's my wave function, and so I'm just making this up because I know it should look like some kind of dome. So I just came up with some arbitrary dome. And so this top part right here I can see is going to be a to the 4. You just plug into that formula. Okay, so this is my guess based on sort of intuitive reasoning. That's my guess. And so now now we want to find we basically have to find the expectation value of the well, what we want to do is we want to find basically the ground state energy and the ground state wave function. But to find the ground state energy, we have to first calculate the expectation value for this wave function. And so let's do that. And so is this wave function normalized? Yes or no? For where a is arbitrary, is it normalized? Yes or no? Somebody tell me.
No?
That's right. It's not. It's just an arbitrary. I don't even know what a is. It's arbitrary. So that means that I got to do it. I got to do it like this. I got to calculate this because that normalizes it for me. All right. And if that doesn't make sense, think about it. And that's not too hard to understand if you think about it a little bit. So I got to calculate the expectation value like this because it's not normalized. And so then let's calculate it. So let's just grind through this. So it's going to be this. It's going to be the integral of psi star of x. And then I got my Hamiltonian, negative h bar squared over 2m squared dx squared plus 1/2 m omega squared x squared. And it's acting on psi of x dx. That's the top part. And then the bottom part is going to be the integral of psi star of x psi of x dx. So that's what I got to do. And I'll just keep reminding you, this part is for normalization purposes. So this is what we got to calculate. And so now what I have to do is, so you see that there's going to be then 3 terms that I have to calculate. And let's calculate them. Although I'm going to skip some steps because it's kind of tedious. But you can see there's 3 integrals to do. So let's do the first integral, which is the easiest one. The first one is the one on bottom. And so that's going to be the integral of psi star psi dx. The one on bottom is going to be the integral. And what are the limits? What are my limits of integration? Somebody tell me.
Negative a to a.
Exactly. And it's going to be this function, x squared. Yeah. I mean, it's squared, so I can just do the order differently. A squared. And it's going to be to the 4th power dx because it's psi star psi. Okay, and that's it. And so that integral is a pain in the ass. You got to expand the polynomial and do it, but it's not that hard. And so if you do it or plug it into your Mathematica or whatever it is that you use, you'll see that it's equal to this: 256 times a to the 9th divided by 9 times 7 times 5. Don't ask me why it's 9 times 7 times 5. I have no clue. That's just the thing I copied out of a book. But that's what it is. That's what Mathematica would give us. Okay, and so then let's do the second integral, which is going to be the second easiest one, which is going to be the potential energy term, which will be integral psi star 1/2 m omega squared x squared times psi dx. So I got to calculate that. So I got to do it. It's 1/2 m omega squared integral from negative a to a. Then I got to have my potential energy term, x squared, I got to have my wave function term, x squared minus a squared to the fourth power dx. And so now you have another annoying integral to calculate, but you can do it. It's not hard. It's just the integral of a polynomial. You guys know how to do that. And so suppose you do all that, then what you'll get is this 1/2 m omega squared times 256 a to the 11th power divided by 11 times 9 times 7 times 5. I don't know why it is that. That's what I copied out of the book. Okay, then we have the third term. And the third term is going to be the kinetic energy term. So I guess I'll call that the potential energy term. This term was the normalization term. And now we have the kinetic energy term. And the kinetic energy term, of course, is going to be negative a to a of psi star, negative h bar squared over 2m, d squared dx squared times psi dx. Okay, so then I got to plug all that in, and that's a big pain in the ass, and I'm not going to write it all out, but once you do some algebra, you're going to find that it looks like this. It's going to be 256 times a to the 7th over 7 times 5 times 3 times h bar squared over 2n. Okay, so that's what you'll get if you do that algebra. And so then just add it all up, and we get this. We see that our expectation value, and the expectation now is a function of what variable? The expectation value of the Hamiltonian is now a function of what variable?
A.
Right, A. That was the variable that I made up. That was I forget, the better word for it, but that's the variable that we have to minimize with respect to. And so when I add everything up, this is what we get. We see that we have 3/2 h bar squared over ma squared plus when you just do a few lines of algebra that I'm skipping, 1 over 22 times m omega squared a squared. Okay, and so okay, so this is my expectation value of my Hamiltonian, and so I know that this is greater than or equal to the energy of the ground state for any A. So no matter what A you plug in there, it's got to be that. The theorem we proved tells us it's got to be greater than the ground state energy. So let's find the A that minimizes this. So let's bring the upper bound all the way down as far as we can go. So then let's minimize with respect to A. And the way we do that is let's take the derivative of h of the expectation value with, and just to be clever, let's do it with respect to a squared instead of a. It's just a little mathematical trick. It makes the math easier. And when you take that derivative, it's going to be negative 3/2 h bar squared over ma to the 4 plus 1 over 22 m omega squared. And I set that equal to what?
0.
That's right. And so then I set it equal to 0, and then I solve this simple equation. And when I solve it, I get a squared is equal to square root of 33 times h bar over m omega. And now, okay, so now I got this weird thing, a squared equals this, square root of 33, blah, blah. What do I do with it?
Plug back into expectation value.
Exactly. Plug back into the expectation value. That's exactly right. And when you do that and do the algebra, what you'll see is that you're going to get H is equal to 1/2 H bar omega times square root of 12 over 11. And what's the true value? Somebody tell me the true value of the ground state.
1/2 H.
Yeah, 1/2 H. Yeah, 1/2 H bar omega. Sorry.
Exactly. I know so many of you knew that. I know. 1/2 H bar omega. That's exactly right. That's the real answer. And so look at the answer we got. It's only 5% off. Isn't that amazing? It's like we just, boom, we just brute force it. We got the ground state. And notice that it's bigger. It's an upper bound. Notice it's bigger. And so I just want you to appreciate what we just did. It's just, you know, it was kind of a pain in the ass, you know, a little bit of algebra, but it was like 20 minutes of work, you know, or half an hour of work, and you just get the answer. So that's pretty powerful. I'm hoping you can appreciate that. Okay, now let's do another example. So that is one example, but now let's do like a really hard problem. Now let's do like a really hard problem. So we're going to use variational principle to solve a really hard problem. And the really hard problem is the ground state of helium. And what we want most is, let's find the ground state energy. Solve for ground state energy of helium. Let's find the ground state energy of helium. And this is a genuinely hard problem. This is hard. So what does the ground state energy of helium equal for helium? And you guys remember what helium is. Helium is this guy where we have 2 protons, and that creates a Coulomb potential. And then we get some states, and then we put 2 electrons in this ground state, and they have to have spin up and down, and we have to symmetrize the wave function. Symmetrize. We've discussed that because there's 2 identical electrons. Because there's 2 electrons. Okay, so that's helium. We've discussed helium before in this class, so you guys kind of remember. And so we want to talk about, and so let's think about it sort of. So these are the 2 electrons, and what happens is we can measure it experimentally. Even without knowing quantum mechanics, we can measure the ground state energy experimentally. Does anybody have an idea of how you actually do that experimentally, what that even means? How would you measure the ground state energy of helium? What would you do?
Could you do it by like looking at like excitations and like transitions between energy levels?
That's right. That's right. That is what you would do. But the transition between the ground state and what? Like, how do you actually find the energy of the ground state?
It would be from like ionized to recombined.
That's right. That's exactly right. So because that's right. That's totally right. So here's my helium. I have 2 electrons there. I won't draw the spins. And so this is the vacuum level. E equals 0. At E equals 0, we're free. Be free, little particle. We're free if we can get there. And so you got to catch a ride on the Underground Railroad. And so here it comes, and someone's got to get these guys out. Be free, little electrons. So you got to dump in some energy somehow, either by light or other electrons, collisions. Somehow you got to give it some energy. And the question is, how much energy did it take to free both electrons? So what is the amount of energy that it takes to free both of those electrons?
It would be 2 times the ground state energy, right?
No, that is the ground state energy. Because it's that binding energy. That is the ground state energy. So if it takes delta E to free them, then the ground state energy is equal to, can someone tell me? There's a little trick. What's the trick?
It's not delta E divided by 2 or something?
No.
Is it negative delta E or something?
That's right.
Okay.
Yeah, because the ground state means that they're bound. It's sort of like, in hydrogen, we have negative 13.6 electron volts, that the electron is bound by that. And so these 2 electrons are bound. So I got to somehow pump enough energy into helium so that the 2 electrons jump out. And when they jump out, they got to have no more energy, just enough energy to get out and not to move, but just to be still and free. And that energy is the ground state energy, if that makes sense. Okay, so it's just like hydrogen, but now 2 electrons instead of 1. So people have done that experiment, and people have figured out, the experimentalists figured out that the that the ground state energy, I'll write it like this. People have figured out that the ground state energy is negative 79 electron volts. Okay, so that's an experimental fact, even without quantum mechanics. Just do it, and you figure that out. So what we want to do now, as little theorists in training, we want to figure out how to explain this. How do we explain this? How do we calculate it? We want to explain this experimental fact, and so let's start thinking to ourselves. So the simplest thing to do, well, let's draw a picture. So first, let's draw a picture. And when we draw the picture, this is what the picture looks like. We got our, actually I don't want to do it like that. We have this, we have our proton that has plus 2e, right? And then we have, we're going to have electron 1. And so this is going to be the position of electron 1. And so I'm going to call this R1. And then I'm going to have electron 2. And then this is going to be the position of electron 2, R2. And so let's put nucleus at 0. Nucleus at R equals 0. And let's assume that it's stationary. Let's assume that the nucleus is stationary because it's so massive. Okay, that just makes it easier. And then we also have this distance between them, which is, there's a vector that I can define like this, which is going to be R1 minus R2. So this is the situation. This is a helium atom. Helium. That's what it looks like, classically. And we always start classically. I've said that before, but when we're talking about energies, because we want to know, we want to draw the picture because we want to understand where does the energy come from. And so we have to figure out what the Hamiltonian is. And to figure out the Hamiltonian, then we always go to classical mechanics. That's where we start. And so from classical mechanics, this is the picture you would draw. Okay, so but now we got to go to quantum mechanics. And so what is the Hamiltonian? So H for helium, let's write out the Hamiltonian. So, okay, what is what is the Hamiltonian? Let me write it like this. It's going to be, you see, I have electron 1, I have electron 2, but I also have the interaction between them. So that's my Hamiltonian. But what are these parts? What is H1? What somebody tell me, what's H1?
P1 squared over 2me, and then plus the Coulomb potential between the nucleus and E1.
Exactly. That's exactly right. And this is the Coulomb. It's minus 2e squared over 4 pi epsilon naught. And what's the next variable?
R1?
Yes, that's right. So that's it. That's good. And P1 squared, of course, is going to be negative. That's going to be, let me erase that. That's going to be negative h bar squared over 2m d squared dr1 squared, right? Because it's going to be, or actually, I'm sorry, I did that wrong. It's going to be, I can write it more elegantly. It's just going to be delta 1 squared as a gradient squared. Okay, that's the kinetic energy. That's right. Plus, and now let's do the same thing for the second electron. And so that's going to be P2 squared over 2m minus 2e squared over 4 pi epsilon naught r2. And this term is going to be negative h bar squared over 2m del 2 squared. Okay. Now let's do the last term. What's that? What's the energy of interaction between the electrons?
E squared over 4 pi epsilon naught R1 minus R2.
Perfect. That's exactly right. That's right. And so that's the interaction term. Okay. So then what we got to do is solve the Schrodinger equation. That's what we got to do. And this is the Hamiltonian. So this is a genuinely hard problem. Okay, this is a hard problem. So there's really, but you guys actually know what to do. There's two obvious things to do that you have learned from class. So what's the first thing that we should do if we want to solve this problem? So the question is, I'm asking you a question. The question is, what is E ground state and psi ground state? This is my question to you. And how do you answer it? What's the first thing that you should do?
Guess a wave function.
Sure, we can guess a wave function, but before guessing a wave function, there's something even simpler. I think what you're doing is you're going through the variational principle, but I'm asking you to do. I'm asking you, don't use the variational principle yet. Do the simplest thing that you've already learned in class. Maybe it's a trick question, but what is the simplest thing we could do?
It looks like a hydrogen atom, and it looks like a perturbation. So you could probably do something like that to make up for that 2 on the potential.
Yeah, we could do perturbation theory, right?
Yeah.
Okay, what's even simpler than that? I want something even simpler than perturbation theory. Maybe it's a trick question, but it's not really a trick question. It's a real question. What is the simplest thing we can do to solve this problem?
We can, I guess you can break off the first 2 terms in H prime to the hydrogen wave function, and just make the substitution to make up for that 2 and wherever the E squared comes up in the energy formula, I guess. And then you can use variational principle to find the last term with the potential.
Wait. I'm saying don't use variational principle. Don't use perturbation theory. What's the simplest thing we can do? Simple. I'm asking for something really simple. But it's worth thinking about. That's why I'm harping on this. What can we do that's to answer those questions without variational principle, without perturbation theory? What's the simplest thing? And we've done it before.
Solve the Schrodinger equation.
Yeah, but for what? This is the Hamiltonian. How can we solve the Schrodinger equation for that Hamiltonian? It's too hard. What can we do to make it easier? Okay, I mean, I'm actually giving you guys a hard time about this because this is very important, because like out in the real world, people are, are faced with hard Hamiltonians every day, and they're always way too hard to solve. And so out in the real world, what people do is they're always trying to simplify the Hamiltonian by making gross approximations. And so the first thing you can do is make a very gross approximation. Make it just so gross, just like so gross you can barely even stand to look at it. Make a gross approximation, and that's what I'm asking you to do. And that's the first thing you should always do. Make the grossest, to solve a problem. It's a hard problem, but you always make a gross approximation to try to solve it. And oftentimes your approximation might be too gross. It might be too big of an approximation, and that means you have to go back and do something else. But you should always start with the simplest thing. So what is the most gross approximation we can make? Somebody tell me.
Can I just throw out the interaction between the electrons?
Yes, exactly. Set the interaction term as 0. That's exactly right. That's it. And so maybe lots of you already thought of that, but that's what I wanted, because that's really the first thing to do. And so now you have that's exactly right. And that's where you should start. You always start the simplest thing. Just make a big approximation. So H is equal to H1 plus H2. Now you know what to do, because that's like from the first week of class, we discussed this. It's just a two-particle Hamiltonian. And so you know that the wave function psi of R1, R2 is going to be equal to psi of ground state for the one body problem, R1, psi of ground state of R2, and then you got to do your symmetrization business. So what's the ground state? First, let's do the ground state. Here's hydrogen. Here's all the levels of hydrogen. This is the ground state right there. What are the quantum numbers of it? N, L, M. What are they? What are they for the ground state?
100.
Yeah, 100. That's right. So I got psi 100, psi 100. I'm putting the 2 electrons into that ground state. But to anti-symmetrize the wave function, I got to do a spin. And so what's my spin state? I got to make it, yes? Yeah?
Oh, I said anti-symmetric.
Right, but what is the anti-symmetric spin state for 2 electrons?
The singlet?
Yes, it's got to be the singlet. Right. Up, down, minus, down, up. Okay, there it is. Okay, so that's the ground state. And let's put some flesh on the bones here. And so we see that the spatial part, because there's no, let's just consider the spatial part. Oops, spatial part. So the spatial part will be psi R1, R2 is equal to psi 100, R1, psi 100, R2. Okay, that's the spatial part. And so let's remind ourselves what psi 100 is. And I will remind you. This is something that you learned last semester when you did the hydrogen atom. You said for hydrogen-like atom with a nucleus of Z, electrons in the nucleus, you guys calculated last semester that psi 100 of R is equal to 2 over square root of 4 pi times Z over A naught to the 3/2 times E to the negative ZR over A naught, where A naught is equal to the Bohr radius, which is equal to 1/2 of an angstrom. Teeny tiny little thing, and you guys and Z is equal to charge of the nucleus, charge of nucleus, and you guys know that the energy of this thing is equal to Z squared, right, times negative 13.6 eV. Okay. So that's the energy, and that's the wave function. So you guys, so that's it. So that means that we're done. I mean, so what we could do is we could just figure out, so then we could just say psi is equal to those two, that thing squared. It's going to be psi 100 of R, well, it's just going to be that thing squared. So let's just multiply these two guys out, right? It's just going to be this thing. And so let's multiply it out. And so it's going to be, so psi, let's write all the variables. R1, R2 is equal to Z cubed over pi A naught cubed E to the negative Z times R1 plus R2 divided by A naught. Okay, so that's the wave function where Z is equal to what again for helium?
2.
That's right. And then the energy is going to be just E1 plus E2, which is going to be, it's going to be twice times Z squared negative 13.6 EV, where again, Z equals 2. Okay, so we got it. You get, see, that's really simple. That was simple. You know, we just ignored the interaction, and it was non-interacting electrons, and we can write down the wave function, and we can write down the ground state energy. Boom, 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 boom. Very simple. So now we just add it up and calculate it. So it's going to be 2 times Z squared is 4 times negative 13.6 EV. And when we do that number, we see that it's going to give us a number which is negative 109 EV. Okay, that's the number we get. But then we look at the experiment, and the experiment is negative 79 EV. So we say this is too big of a discrepancy, too big of a difference. And in the real world, basically what you'd be doing is you'd be, as a physicist, it's like in the real world, what would happen is you're an experimentalist, you measure how much energy it takes to take those 2 electrons out of helium, and you go, oh my God, it's 79 electron volts. That's so cool. I measured it. And now I want to write a paper about it. And so you write, but to write your paper, you have to analyze your data. So you made the measurement, and now you have to explain it. So as an experimentalist, you just want to do the simplest thing. And so you're like, okay, let's try to explain this number, 79. So I'll do the simplest thing. I'll just ignore the electron-electron interaction and calculate it. And then you calculate it like we just did, and you get this number, negative 109. But then you look at your experimental number, 79, and you're like, shit, that's like 50% off. I mean, 40% off. That's like a really big discrepancy. I'm not going to be able to publish my paper in a high-impact journal if the match between experiment and theory is so shitty. so terrible. I got to get a better match, because if you can explain your data, then you usually can publish in a higher journal. That's how it works. That's actually how it works out in the real world. So as an experimentalist, you'd be like, man, I want to explain it better. I got to get it. If I can explain my data better, then the referees will be happier, and I'll be able to publish it in a higher impact journal. Okay, so we must do better. The approximation was too gross. Approximation was too gross. So we got to do something better. Okay, what's the next thing we do? And you know the answer to this. The non-interaction didn't work, so what's the next thing we do? Well, look at this. I can write H equals H naught plus H prime. H prime is equal to what?
The electron-electron interaction.
Exactly, negative E squared over 4 pi epsilon naught R1 minus R2. That's exactly right. And H naught is just going to be my H1 plus H2. Okay, so you can formulate the problem in this way. What am I using here? What is this called?
Perturbation theory.
Exactly, perturbation theory. And so what I would say then is that the energy is equal to E naught plus, actually, what is the right? I would say it's E naught plus E prime. And E naught in this case is going to be the negative 109 EV. And what's E prime? How do I get E prime? Do you guys know how to get, how might you get E prime using perturbation theory?
Take the expectation value of H prime with respect to our basis from the previous
That's right.
calculations.
Exactly. And this is just going to be our, psi 100 R1, psi 100 R2. Exactly. Yeah, that's what you do. And then this kind of goes in there. So that would be the next thing that you would be. That would be the next logical thing that you do to explain your data. And this is going to give you a positive number. It will, because did I just screw that up? Where's my Hamiltonian? Yeah, because this is a positive number, not negative, because the two electrons repel each other. So this will be a positive number. And so you can see already that this is going to help you, because because you had too much binding energy. And so this will give you some positive energy because of the repulsion of the electrons. And that will make your answer closer to 79. So that would be the next logical thing to do. But let's not do it. Today, we won't do it. But I'll say, so this would be the logical thing to do, but today we won't do it. Instead, what we're going to do is we're going to use the variational principle. It turns out that for this particular problem, the variational principle is better. But it's not obvious why it's better. Okay, it's not obvious why it is, but it just is. But that doesn't matter. This is just an example to see how to use the variational principle. So let's use the variational principle. And so to use the variational principle, what we got to do is today we won't use perturbation theory. We're going to use the variational principle instead to solve this problem. And so now let's do the variational principle for helium. Variational principle. So how do you, for helium, and what's the first thing I got to do? What do I have to do?
Guess the wave function.
Yes, that's exactly right. I have to guess the wave function. Now, guessing the wave function, as I said before, that's sort of, not obvious how to do that. And so basically you have to use your physical intuition. Use physical intuition. And the physical intuition comes from this. Because look, we see here that this is the non-interacting wave function. Non-interacting wave function. And so let's write that down. Psi of R1, R2 is equal to Z cubed over pi A naught cubed e to the negative Z R1 plus R2 over A naught. Now, normally we would say for no interactions, then we would say that Z equals what? Well, what is Z? For helium.
Is it 1/2 or something?
What?
Is it 1/2 or 1?
No, remember Z.
Oh, for non-interacting, 0. Yeah, right.
No, Z is this. It's the this is the Z here, see? Right here?
Oh, yeah.
That's Z. So Z is the charge of the nucleus. Okay? So what is Z for the
2.
normal case? Yes. Exactly. Because it's helium. Since helium. But what we're doing now is we're staring at this. What we're doing is let's stare at this wave function, and let's ask ourselves. We have to ask ourselves for the variational principle. We need a wave function that has a variable. It's a function, but it also has like some new variable in it. And so the question will be, what should the new variable be? What should the variational factor be? What is the factor that we will vary? What should the variational factor be? And it's not R1 and R2, because those are just the normal variables of those are the normal variables of the wave function, you know, the position of the electrons. I'm not talking about those variables. I'm saying, what is the variational factor?
Would it be the Bohr radius, A naught?
That's good. That's a good guess. Yes, that would work. You could pick the Bohr radius, and you could just say, let that be the variational. Let that be the variational factor. That's good. That would work. But traditionally we don't do that. We do something different. What do you think the other thing is? There's not many choices. Instead of doing the Bohr radius, what do we do instead?
Z?
Yes. We use Z.
Oh, and it would behave like an effective charge or something like that?
Yes. That's exactly right. That's right. So Z equals an effective charge, exactly what you said. And this is physical and intuitive, and the reason it makes sense from just an intuitive point of view, and you can sort of see how to solve a physics problem, you need to have some intuition, right? To use the variational principle, you require some intuition. So look, just picture it in your mind. This is helium. I have some electron here, and then I have another electron here. Now, this is Z of the nucleus. And so you'll notice that, let's say if this is Z equals 2, normally this electron would see, if the other electron wasn't there, then this guy would just see the Z equals 2. But because this electron is there, this electron sees really Z or equals around 1, because it's screened, although it's not exactly 1, because it's sort of like I have the nucleus here, which has +2, but now I have my first electron, and then I have my second electron. And so wherever this second electron is, he will always see some negative charge in front of that nucleus. So effective charge is going to be, well, I'll ask you, is it going to be less than or greater than 2? Do you expect the effective charge to be less than 2 or greater than 2?
Less than?
That's right, less than. Because it's, and the term we call that, we say that this electron is doing something to this electron. Do you guys know the word that we use? This is an electronic process. Do you guys know what the word is?
It's screening.
Exactly. This is screening. This is the effect of screening. One electron screens the other. And so because of screening, then we use this wave function, and we say that we use Z as the variational factor. So now it's back to the variational principle, and so let's just calculate it. So now, so now we have a wave function, and so now we just have to solve for the expectation value. H is equal to psi H psi psi psi. We got to just calculate now. Because now we have a wave function. Psi is and the variable is v of r1 r2 is equal to z cubed over pi a naught cubed e to the negative z r1 plus r2 over a naught. Okay. And so this is going to be a function of z. We got to calculate that, and then we're going to take the derivative with respect to what variable? Once we calculate it, we're going to get some messy function. We're going to take the derivative with respect to what?
Z.
And we're going to set that derivative equal to what?
0.
And that will give us the z min. And then we're going to take the z min, and what are we going to do with it?
Plug
it back in.
Yes, plug back in. Yes, and then we will have our answer. Then that will be our upper bound on the ground state energy. So that's what we're going to do. Let's do it right now. So do you have a question? Okay, so let's just do it. And so we see, so now we got to write out the Hamiltonian, and so it's kind of messy, you know, because we see then that one thing that's nice is that it's already normalized. So we don't have to do that normalization thing, because we're using these functions that we got from last semester. It's already normalized, and so H. So it's just, all we got to do is calculate this, psi H psi, which is going to be equal to the integral over the position of particle 1, the position of particle 2, psi star of R1, R2, Hamiltonian, acting on psi R1, R2. Okay, so that's all we got to do, just calculate that integral. But it's tedious, it's a pain, but we can make it easier because we see that H, we can write the Hamiltonian in terms of three pieces. It has an H1 plus an H2 plus an H, the interaction term, which I'll call EE, since the electrons are interacting with each other. And so then when I calculate the expectation value of H, I can do them separately, H1, H2, HEE. And and when you look at it, you feel like this should be, there should be a trick, because the wave function that we're using is so close. The wave function psi z is almost an eigenstate of H1. It's almost an eigenstate, but but the reason it's not an eigenstate is because H1 needs z equals to what? What is z? What is the charge on the nucleus? What?
2.
Yes. To be an eigenstate of H1, you need z to be 2. But we are now using z as a variable. So this is what we're going to do. We're going to do a silly little trick, which is very cute. We're going to say that H1, which we know what it is, it's P1 squared over 2m plus minus 2 ZZ E squared over 4 pi epsilon naught R1 squared. We're going to do a little trick. We're going to say plus Z E squared over 4 pi epsilon naught R1 squared minus Z E squared over 4 pi epsilon naught R1 squared. And this is the old add 0 trick. We can always add 0 to anything, right? And then we notice that this is equal to H1 plus, this is the big trick, Z minus 2 E squared over, I'm sorry, H1 prime over 4 pi epsilon naught R1. Oops, I shouldn't square those things. This is the big trick, where this is the Hamiltonian. This is the Hamiltonian for arbitrary z. Do you see that? So I can write H1 is equal to H1 prime plus that extra term. And the reason I did this is because now the expectation value of H1 is equal to the expectation value of H1 prime for our psi sub z plus the expectation value of the extra term for our psi sub z. And what is this? What is the expectation value of H1 prime? Where I should write here, where H1 prime is equal to P1 squared over 2m minus Z E squared over 4 pi epsilon naught R1. That's what H1 prime is. See, this was H1, this. But this is H1 prime. What is the expectation value for H1 prime? It's a trick. Because H1 prime is acting on this wave function. Where's my wave function? Here's my wave function. See that wave function? I have the stars here. H1 prime is acting on that. What is the relationship between this wave function and H1 prime? What happens when H1 prime hits this wave function? Can you guess? Can anyone guess?
it returns the traditional energies for the hydrogen wave function, except wherever you see a E squared, you multiply that times Z.
Yeah, that's exactly right. It gives us Z squared times negative 13.6 eV, because this is the eigenstate. Because this thing here is the eigenstate of H1 prime. That's the whole point. It is kind of a trick. And so what that means then is that this thing becomes Z squared times negative 13.6 eV. And so that means then that it becomes easier to calculate the expectation value of H1 because now I only have to calculate the expectation value of the extra term, which is easier. So let's put that together. And so what we have then is H is equal to, now I can write it like this, H1 prime plus H2 prime, and these are the Hamiltonians for Z, arbitrary Z, plus I have my Z minus 2 E squared over 4 pi epsilon naught R1 plus my Z minus 2 E squared 4 pi epsilon naught R2 plus now I have my interaction term, which is positive, plus E squared over 4 pi epsilon naught R1 minus R2. And so now when I calculate the expectation value of H, I just got to calculate the expectation of all these guys. And these guys are simple. They're going to be equal to minus Z squared 13.6 eV, and this one is minus Z squared 13.6 eV. And these ones, this one is going to be actually pretty easy, because when I do the integral, then that integral is going to be it's going to be basically Z minus 2 E squared over 4 pi epsilon naught, and it's the expectation value of 1 over R1 for that wave function. And that's actually an easy integral. And so when you do, but I don't have time to do all the details, but when you do that integral, it's going to be Z over A naught. And it should remind you of you get it from the virial theorem. So that integral is actually really easy. And then the only integral that you still have that's hard is this one. This one is hard. So basically you've reduced the problem, so we got all those terms we know, they're really easy except for the last one. And the hard one is the last one. We have to calculate this hard one, and I'm not going to set it up. It's in the book, but the expectation value of the interaction term is a hard integral. It's going to be, I'll just write the integral for you, E squared over 4 pi epsilon naught Z cubed over pi A cubed times the double integral of e to the negative Z R1 plus R2 over A naught over R1 minus R2 d cubed R1 d cubed R2. So this is a hard integral, but the book shows how to do it. It's a famous integral. You see it in E&M as well. You can find it in the book. Find it in book And when you work it all out, you see that it's equal to 5z times over 4 times 13.6 eV. And so when we put it all together, what we have is h as a function of z is equal to negative 2z squared plus 27 over 4z times 13.6 eV. And then if you take dh dz and set it equal to 0, then what you'll find, and I'm just sort of rushing now just to get it done, but we find that z is equal to 27 over 16. And notice that this is less than 2. And then plug back in. If we plug back into h, then what we get is that h, the expectation value of h for our psi is equal to negative 77.5 eV. That's the number you actually get when you do all the details. And so notice that so this is negative 77.5 is greater than negative 79, but it's pretty good. It's only 2% off. So we just solved a really hard problem, a significant problem using the variational principle. I'm sorry I went a few minutes over. Okay, folks, I'll see you on Thursday. Bye-bye.
Thank you, Professor.